For dissociation, H nu is equal to 2 H nu E xe into V plus 1, and this should be equal to 0. This implies V plus 1 is equal to half xe, hence we can obtain V. We can then use equation EV is equal to, open bracket, V plus a half into H nu E minus H nu E xe into V plus a half, close bracket, squared, plus H nu E xe, open bracket, V plus a half, close, cubed, and so on and so forth, to estimate bond dissociation energy. This is how we do it. As shown in this diagram, the dotted line shows the simple harmonic oscillator, whereas that curve shows the anharmonic oscillator. As can be seen, the separation between 0 and 1 is much bigger than 1 and 2, which is also bigger than 2, 3, and 3 and 4, and so on and so forth. For a given type of molecule, the greater its potential curve deviates from simple harmonic oscillator, the less the energy to cause dissociation. The anharmonicity of the molecule leads to the breakdown of the selection rules. For a simple harmonic oscillator, delta V is equal to plus or minus 1. However, for anharmonic oscillator, we have delta V being equal to plus or minus 1, plus or minus 2, plus or minus 3, or plus or minus 4. Still, the most important transition is 0 to 1, the fundamental. But for the anharmonic oscillator, the following transitions are also now possible. 0 to 2, this gives the first overtone. 0 to 3, which gives the second overtone. 0 to 4, which gives the third overtone, and so on and so forth. The fundamental transition will still remain the most intense. This is because, from Boltzmann's distribution, most molecules are in the ground state at room temperature. It was pointed out that for a linear molecule, the degree of vibrational freedom can be given as n is equal to, open bracket, 3n minus 5. Whereas for other molecules, that's the nonlinear ones, n is equal to, open bracket, 3n minus 6. Here, lowercase n is number of atoms in the molecule, and capital N is the degrees of freedom of vibration. The degrees of vibration of freedom correspond to ways in which the molecule can vibrate. Let us look at an example of the water molecule. Here you have the oxygen linked to the hydrogen and linked to the other hydrogen. As shown by the arrows on the molecule, we can have that vibration and that vibration and that stretching vibration all at the same time. That means the molecule is undergoing a symmetric stretching, which is the same in all directions. Now, this absorbs at 3,652 per centimeter. That's where we will find a peak for that mode of vibration. Let us go to a slightly more complex one, the antisymmetric. Now here the oxygen is vibrating in that direction while the hydrogen is vibrating in this direction while the other hydrogen is stretching out. So it's a compression plus a stretch plus a stretch. much more complicated. Still the frequencies are the same and in phase, but this one will absorb at 3,756 per centimeter at a much higher energy level. Let us look at the bending modes. This involves altering the bond angle and requires less energy than those above, i.e. it occurs at a lower frequency. So whereas that hydrogen is bending, that is moving that way, the oxygen is moving this way, and this hydrogen is moving that way. And this one absorbs at 1,595 per centimeter. Each way of vibration has its own frequency corresponding to the different energy level, the one with low frequency being the most intense. So for water, we have that, and this one. In practice, molecules will vibrate in a complex manner, which can be resolved into a small number of normal vibration modes, equal to the number of degrees of vibrational freedom. In the spectrum, we also observe combination bands. These arise from two or more frequencies being excited together. These different frequencies correspond to different modes of vibration. For instance, we have the binary combination where you have mu1 plus mu2 to give you a band, and mu3 plus mu4, or mu2 plus mu3. These will give rise to peaks due to binary combinations. We can also have ternary combinations, that's mu1 plus mu2 plus mu3, all combining to give you a band. It must be pointed out that bands due to these combinations are very weak. We also obtain difference bands due to loss of one frequency and gain of another type. Let's try out this question. What is the 0-point energy of a diatomic molecule with a fundamental vibration frequency of 3 times 10 to the 14th Hertz? Try out a solution. E is equal to mu plus half h omega E, which means E is equal to 0 plus a half into 6.626 times 10 to the minus 34 times 3 times 10 to the 14. And that gives you 9.94 times 10 to minus 20 joules. Another question. Calculate the fundamental vibration wave number of gaseous H1Cl35, given that the force constant for the stretching bond is 516 newtons per meter. Solution. Here the reduced mass of mu of HCl is given by mu is equal to mH times MCl over mH plus MCl, which when we substitute gives you that. The fundamental vibration wave number is given by mu is equal to omega E over C, which is equal to half pi C times the square root of open bracket K over mu close. Substituting gives that, and finally gives us the frequency of 2,990 per centimeter. Let us now summarize. The selection rules delta V is plus or minus 1, plus or minus 2, plus or minus 3, different from the rotational system. The electric